for attending this talk. I'm going to talk about our tool Pufferfish today. This is a joint work with Hitseq Sarkar with the help of Avi Srivastava under the supervision of Professor Rob Patro. So searching in a database of sequences is a fundamental task in computational biology, and it's the starting point for so many different analysis and applications, such as alignment and mapping, quantification, abundance estimation, or metagenomic analysis. So if we want to put, we can put all different types of indexing tools and indexing data structures that we have in 4 different categories. The full text indices are space efficient, but because of not being cache efficient, they have a large constant penalty at the query time. And hashing-based indices, on the other hand, have pretty fast queries, but they grow large very quickly. Recently, there's been a move from linear-based indices to graph-based indexing, that instead of indexing each reference independent of the rest of the references, we put all of the sequences of references in a graph, which is a natural way of representing a set of related sequences. So to overcome this trade-off of space and time between the linear self-indexing and hash-based indexing schemes, we thought of another indexing data structure that maintains a space, a moderate space, but is as quick as hash-based indices regarding the query, which can be used in so many different analyses on large connections of genomes, such as metagenomic analysis. So our indexing data structure is on top of a compacted de Bruijn graph. Let me quickly walk you through what a compacted de Bruijn graph is. The compacted de Bruijn graph is derived from a de Bruijn graph, which in a de Bruijn graph, each node contains a sequence for a k-mer. And compacted de Bruijn graph comes from a de Bruijn graph by combining all the k-mer nodes in a non-branching path into one node, so that we can overcome the overlaps of k-1 between the nodes. To get the list of references and the position and orientation of each sequence in the nodes that we call Untitled, we maintain this Untitled information table, and for each row corresponds to one of these Uniteds and contains the list of all the references that the sequence appears in, and the orientation and the position of that sequence. So this is an overview of our pipeline, Pufferfish Pipeline. The main data structure happens in this box, but we offload the construction task of compacted de Bruijn graph to one of the existing tools for building compacted de Bruijn graph from a set of FASTA files. We specifically use Tupaco because it's specialized to build a CDBG for a set of references. And then the input to this data structure is a compacted de Bruijn graph, which is slightly modified through this pre-processing step. So there exist other tools that build an index on top of a compacted de Bruijn graph, such as Callisto and DBGA. What they do is that they store all the set of distinct k-mers in a hash table. And then the value corresponding to each key is the Untitled that this k-mer belongs to, and the position of that k-mer in that Untitled. But the problem with a traditional hash table is that they're big. You need to spend at least 2K bits to store just the key, which are k-mers, and then some extra bits to store the values associated to that k-mer. So what we do in Pufferfish is that, based on the characteristics of a compacted de Bruijn graph, which is specifically uniqueness of k-mers in a compacted de Bruijn graph, we thought that minimal perfect hash function is a reasonable and efficient choice for hashing these k-mers. So minimal perfect, I'll quickly go over the properties and some restrictions of a minimal perfect hash function. So minimal perfect hash function outputs a unique index between 0 and n, where n is total number of distinct k-mers as input to this hash function. There is no collision between the set of outputs, meaning that we have a unique index per each input, and we just spend a few bits per each k-mer independent of the length of the k-mer and what the k-mer is, what the k size is. But minimum perfect hash function doesn't guarantee not having collision with any input from outside the universe of the input that it was built on, meaning that we might have something analogous to a false positive concept. Meaning that if we search for a k-mer that didn't exist originally from in the set of our input, we might get back some index between 0 to n. And also, it doesn't preserve the order of the input k-mers, so the indices are not guaranteed to be the same order, in the same order as as we give k-mers as input. So to overcome this false positive restriction of minimal perfect hash, we require to have access to the actual sequence of the k-mers to compare the sequence that we get to the original query. So for that, we have this sequence data structure and then the boundary data structure. In addition to that, we put the 2-bit encoded set of contigs in this sequence data sequence int vector, and then we set the bits in the boundary bit vector corresponding to the end of each contig to separate the boundaries of contigs from each other. So in this way, if we can get from this index of 0 to n to the actual position of the k-mer in the sequence bit vector, then we can retrieve all the information that we require for that bit vector, which is the set of references that this k-mer appears in and the position of the k-mer and orientation. In addition to the fact that we can fetch this k-mer, compare it with the original query, and see if it's a false positive or not. So using the succinct rank operation, we can get the index of the unitic that this k-mer belongs to, and then go to the corresponding row and fetch the information for that unitic. Using the succinct operation of select, we can find the origin of that unitic that k-mer belongs to, and hence getting the distance of that k-mer from the origin of that unitic. And in this way, we can actually fetch all the list of references for that k-mer, the position of that k-mer in that reference, and the orientation. The problem is, as I said earlier, because minimal perfect hash function doesn't preserve the order, the output index is not necessarily the actual index of the k-mer. For that, we need to maintain another data structure, which is the position bit vector, where in each index corresponding to the k-mer, we put the actual position of the k-mer in the sequence bit vector. And now the whole pipeline of query is complete. This representation by itself, as you can see later in the slides, is quite space efficient. However, as you can see again in this donut, which shows the space that is taken by different components of our index, the majority of the space by a large margin goes to position bit vector. And that's why we introduced this new idea of sampling and storing the position for just a subset of k-mers instead of all the k-mers. This idea is analogous to the sampling of suffix array in FM index. And we take advantage of the properties of compacted de Bruijn graph, which is that each k-mer appears only once, and hence it has at most one unique predecessor and one unique successor. So there is a unique path from a non-sampled k-mer that can get us to a sampled k-mer, and then all these k-mers along the path exist in the minimal perfect hash function, so we can easily get ourselves to the closest sampled k-mer from both directions and walk our way back to the non-sampled and have the position for that non-sampled k-mer. There is a trade-off going on again, because every time for a non-sampled k-mer, you have more than one query to get and fetch the position of that non-sampled k-mer. And to maintain balance between trade-off of space and time, we practically in our tool allow at most one extra step for the non-sampled k-mers. So for the results, I will show you two sets of results. One are the set of benchmarks on our index, where we look up for k-mers, and I provide you with the space and time that it takes to build the index and query the index. The other is a real application that can be built around, that this index data structure can be used in that real application. So for the benchmarks, we compare our tools against BWA selected from the self-indexing scheme of indices which are space efficient, and the Callisto index, which is from the hash-based indices, which are time efficient at the query time. We run our benchmarks on 3 data sets: small, which is the human transcriptome. All the indices should be able to manage this in a short time and small space. Moderate data set with 3 gigs of reference sequences, and then more than 8,000 bacterial genomes, which is our large data set with 18 gigs of reference sequences. So in the index building benchmarks, we are doing we take more space compared to BWA, but we are much better compared to the hash-based indexing tool, and in a relatively similar time we build our index compared to the other tools for all the 3 data sets. For the lookup, what we did is that we selected a set of reads from each of these data sets, and we splitted all the reads into their constituent k-mers, and then we queried for these k-mers in our index. And as you can see, we take even less space in the query for the lookup, but we still take more space than BWA, still much more efficient than Callisto. And if you take a look at our sparse, while our dense indexing data structure is doing a pretty good job regarding the query time, we can save a lot more space in our sparse version of index, while we don't hurt the query time that much, especially in the larger data set. So as the application, what we did is that we tried our index in the taxonomic read classification on a large set of bacteria. So we adopted the same algorithm as Kraken, which is a popular tool in this area. As you can see, we have a taxonomy tree with different levels of taxonomy, starting from life, and the lowest levels are strain at the leaves. We have a bunch of reads. When we want to query them, we break them into their constituent k-mers. We search for the k-mers. We try to align the k-mers to the lowest level node. If at the end we get a tie to align the read, and it's impossible to align it to one specific node, we search for the lowest common ancestor of those nodes and align it back to that internal node. The only difference here with, between our tool and Kraken or other existing tools is that instead of just looking for the k-mer abundance, we actually, because we have a lightweight mapper around our index data structure, we look for all the consistent chains of matches, which should be consistent in position and orientation. We expect this to give us a better accuracy result at the end. So one of the assessments that we provide is one unique metric over the whole tree. So the truth that we have in our simulated, in the simulated data set that we use, aligns the reads to just the leaves. But we, in our process, will align the read to either the leaves or the internal nodes. What we do is that we aggregate this classified reads from the lowest level to the top of the tree, and then we compare, we compare the nodes from our prediction and the truth at the same levels, and we provide one unique assessment metric at the end for the whole level, for the whole tree. As you can see, we've used 3 metrics: F1, Spearman, and MARD, and in all of these we are doing better in accuracy compared to Kraken and Clark. We've used the simulated data from this paper, and we've used the default settings for running Kraken and Clark. So the future applications that we can build around this indexing data structure is, now that we have this compacted De Bruijn graph, we can align back a collection of genomes to this graph and build an index on top of them and look for different variations across genomes. We can map the reads back to both transcriptome and genome, and index transcriptome and genome together. Hence, we can have an application that search for novel splicing events or does RNA sequence quality control, and we already have a lightweight mapper for pufferfish. We can just improve it to upgrade it to an aligner and use this index in an aligner. I want to thank the institutes that funded us for this project, and all my lab members from Combined Lab and Stony Brook University for their help and support. Thank you.
Questions? So it seems a little bit like pseudo-alignment. I mean, I guess because I see Rob's name on the thing. Is this the same sort of structure, data structure?
Yeah, it's an indexing data structure. We can build a pseudo-aligner or an aligner on top of that, which
so
we've already.
Aligners, what you're suggesting.
Yeah.
Okay, well, that's really cool.
But which takes a smaller space. That's the whole point of this. Yeah.
Thank you very much for your presentation.